Here's a double-sided mirror. It's not just any mirror, however. It's a half-transparent mirror. Any given photon of light has a 50% chance of going through and a 50% chance of getting reflected backward. Pretty simple, right? But what if we have a bunch of these mirrors and shine a flashlight at them? Assuming light moves at an infinitely fast speed, approximately how much of the light passes through all of these mirrors? Okay, first things first, let's simplify the problem. We already know that for one mirror, 50% of the light will pass through. So we'll start with two mirrors. I'll put them down as two lines. Right off the bat, we know that 50% of the light is reflected from the first mirror. The rest makes it in between the first and second mirror, and we now have two cases. The light gets reflected or it passes through. Overall, 1/4 of the light will make it through. However, that's not the end of the story, since the light that's reflected off the second mirror can then reflect off the first mirror, creating an infinite amount of reflections. If we continue the process, it will look something like this. Notice the pattern? The probabilities form a geometric sequence. If we sum each of the probabilities using a formula for the sum of a geometric series, we get that 1/3 of the light will make it through. Okay, now let's try three mirrors. At first, things seem exponentially more complicated. However, we could use what we know about the two-mirror case we did earlier to simplify things. In particular, we can treat two of the three mirrors as a single mirror now. 1/3 of the light will pass through this mirror, and 2/3 will get reflected. In addition, let's do the same thing we did with the two-mirror case and label the probabilities of different rays like so. Notice another geometric sequence? Every next term has a 1/3 term added on. When we calculate the sum of this series, we get that 1/4 of the light will make it through. Now that we've taken a look at three cases, we can see an overall pattern showing up. With one mirror, the transmittance is 1/2. With two, 1/3. With three, 1/4. It seems that with n mirrors, the transmittance is 1/n+1. We can use induction to prove that this is indeed true, the base case being one mirror, which we already know is true. For the inductive step, we assume that the case with n-1 mirrors is true, and use that information to prove that for n mirrors, the transmittance is 1/n+1. Here, I've drawn n mirrors. Similar to what we did with three mirrors, we can take n-1 mirrors and simplify them into a single mirror with a transmittance of 1/n. From here on, we can again label the probabilities. Like before, the probabilities form a geometric sequence with a sum of 1/n+1, thus proving our claim. Thanks for watching. I hope you enjoyed this weird problem.